Esteemed guest this afternoon. Welcome everybody. My name is Gabe Cook. I'm the ciderologist, and welcome to another iteration of the Three Counties Cider and Perry Association's webinar series. After a break of a few weeks, we are back for a series of 4 weeks running of webinars under the title of CraftCon Live. Now, CraftCon was due to be the premier event brought to you by the Three Counties Cider and Perry Association this year after the huge success of its inaugural event last year. Alas, like majority of things between March and now, COVID-19 put paid to the opportunity to host that event this year. Keep your eyes peeled for CraftCon 2021. And CraftCon is primarily a sort of technically focused seminar series due to take place in Worcestershire. And so because that event wasn't able to take place, for these 4 sessions that are coming up every Wednesday, 4 p.m, right here for the next 4 weeks in a row, we have a slightly technical focus. And one of the presenters at CraftCon Live was due to be Dr. Andrew Lee, who joins me now. And for anybody who knows Andrew, you know that he has a long history within the cider industry and is an incredibly important character within the world of craft cider making. He was talking about and utilizing the term craft cider before craft was even a thing in the UK, certainly in its common parlance related to beer, certainly. And many people all around the world, and I can see that we have got West Virginia and that'll be Seattle as well, is already tuning in. The extent of the impact of Andrew's work through the book Craft Cider Making as a really important tome. Everybody understands the value of what Andrew has brought to the global cider industry of the last few years. So Andrew, how are you, my friend? Good to see you.
I'm fine, thank you. Yes, I think I'm coping with the new way of life.
the new normal.
Yeah, the new normal.
So we've got I've given you a little bit of an intro there. I don't think I can probably do it as well as you. But tell us briefly, first of all, before we get into some nuts and bolts of phenolics, what is your sort of association with cider? Why is it that we're sat here talking about phenolics? How have we got to this point?
Well, it's like a lot of things in life. It's a bit accidental, really. I started my career in the tea industry, and I was working on tea phenolics. And I thought, oh, I'd really like to go back to Bristol, where I graduated, and do a PhD. And I wonder if I could wangle it so I could do it on cider phenolics. At Long Ashton, it sounded a good one. And by great good fortune, there was an opportunity to do that. They were actually looking for somebody to work on phenolics, funnily enough. And so I ended up at Long Ashton. I was there for 13 years. So I was working mostly on type tannin, colour sort of issues, which is what we're going to talk about today. I got involved in cider in a much wider sense as well. And then, of course, Long Ashton went belly up in 1985. So I had to find another job, and I ended up working for Cadbury Schweppes, chocolate, soft drinks, and then we set up a consultancy operation called RSSL. And I suddenly discovered that people were sort of coming to me who knew me from the old days and wanting sort of cider stuff done. And well, that's interesting. I can do a bit of consultancy as well. And then at the same time, I was developing my own very, very small scale amateur cider orchard next to my house. I was living in South Oxfordshire by then. And it was sort of the two things going in parallel. I was doing work for the big companies on consultancy stuff. And then I was doing little bits of craft cider making for myself, and gradually the two sort of became almost integrated. And then when people started to when the internet came along, I'd done some articles on craft cider making for a self-sufficiency magazine. It was actually called Practical Self-Sufficiency. It was its original title.
Is this proud tome still in publication?
Well, I think it is. It changed its name to Home Farm after several years.
Okay.
Which is rather sort of more precise.
So somewhere there's an article written by a fresh-faced Andrew Lee.
A series of 6 articles for Practical Self-Sufficiency on cider making. And then when the internet came along, I thought, well, I could dump these things on the internet. I didn't really understand how that was done. Set up a web page. and then it all grew from there. And then I developed the web page a bit, and then got into all sorts of discussion groups as they were developing, and then eventually a lot of the web page stuff became a book because people were nagging me to do a book. So it gradually developed like that, really. And that's
amazing.
where we are today. Yeah.
There's everybody. We're recording on Zoom, and we're broadcasting via Facebook. So I'm manning the. I'm looking at the comments and seeing what's coming in, and there's a lot of love for you, Andrew, and for all of your work from all over the world. Appreciation for your website, for your book, but also for the cider workshop, the original sort of page and group where people could come together and share and exchange knowledge and information about cider making, and it being a very global thing. When I first started looking at the cider workshop, probably 2006 and 7, it was fascinating to have people from Australia and from the USA and from Canada, as well as the UK, talking about some of the technicalities of cider making. So we've got lots of people watching all around. But let's get on to the subject matter for today, which is this behind me. As you can see, I'm within the Phenolics, and I know that, Andrew, you've got a presentation for us. So if you'd like to load up your presentation,
okay,
everybody watching, you'll still be able to see us in the corner here.
Yeah.
Andrew's going to deliver this presentation. If there are questions about any of the topics, then do put it on Facebook, and I will ask Andrew as we go through if it's something that's pertinent. If it's something a bit more general, I might save it to the end. Otherwise, Andrew, it's over to you.
Okay, well, thank you very much, and welcome to everybody. I don't know how many of you there are. I'm very impressed. There are some international entrants as well, so to speak. Anyway, this is what I'm going to talk about: phenolics in cider apples and what they mean for us. So, if I can get the cursor to go correctly. Right, I kind of covered this a minute or two ago, but actually I started my work in phenolics, working for Brookbond Tea, and then I was at Long Ashton for a good many years. And then I moved to Cadbury Schweppes, because one of the things with cocoa and others, and the soft drinks we were dealing with, is that they also have phenolics and tannins, and cocoa particularly. And so, in a way, I kept going professionally with that. So I say that I've been involved with plant polyphenols all my working life, which is true, really, and I never really managed to escape them. Let's see if I can get this to just, yeah, it's the next slide. Okay, so what we need to ask first of all is, what is a phenolic? Now you've got this, let's see if this works as a cursor. Yes, it does. This is the structure of phenol, which is a nasty corrosive chemical that you would not wish to encounter in most of your life. And that is why it derives the name phenolic. And you don't find that in plants at all. But what you do find are the polyphenols, which are derivatives of them. And we'll go through those in a while. So the major groups that you find in apples, at any rate, are the phenolic acids. Florentins and anthocyanins I'll skip because they're not terribly relevant, really. Anthocyanins are pretty and they make the skin red, but they're not awfully relevant in terms of apple and cider processing. So you've got phenolic acids, and then the catechins and the prosanidins, which is a fancy name for what we've always in the past called tannins. And obviously that word comes from the tanning of skins and hides and things, and tannins have been known for thousands of years because they were used to preserve hides for turning into clothing and leather and things like that. So this is one of the phenolic acids, or a couple of the phenolic acids, which we find in ciders. There will be a few structures at the beginning, but don't worry too much about the detail. But just to give you some picture, and if those of you with any chemical background have some idea. You see the phenolic part is still here. This is why it's a polyphenol. This is one of these, chlorogenic acid, and it has another acid called quinic acid as part of it here. But the fact it's phenolic is because of that. And the next one is the catechins, epicatechin, catechin, and they've got more phenolic groups on them here, 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 and here. So they are genuinely polyphenols, many phenols on one molecule. And then we move into the prosanidins, and this is one of the common dimers, prosanidin B2, which is actually an epicatechin dimer. it's widespread in many, many fruits, and you find it in wine grapes, you find it in apples, you find it in a whole raft of fruits which have any tannin in them. And the true tannins then are really these. These are the prosanguine oligomers. So what you've got is you've got groups of epicatechin built up. I think that's the one that Gabe's got somewhat at the back of his head. And you've got these all built up into oligomers, means connections. You've got connections of these things. An oligomer is like a short polymer, if you like. And in apple juice, you get about, from where this factor N, this thing in the middle, if you like, this repeating unit, as we would call it, is somewhere between 0 and 7. So if you had 0, it would just be a dimer because you'd have 2 units. And if you had 7, then you would have an octamer, 8 units joined together. And that's about the maximum solubility that you can get in apple juice, and consequently in cider. But you get a lot of them left behind in the pulp, and there's some very interesting work in France years ago that showed you've even got groups of up to 20 of these left, very long chain polymers left in the apple skin, which just doesn't get extracted because it isn't more soluble. But in real life apple juice and cider, the things that we're interested in are ranging from essentially dimers up to octamers or something like that. Now, you get polyphenols in all apples, but where we find them at the highest levels are in the bitter sharps and the bitter sweets, as we currently classify them. And this is the standard British classification, as you'll know. All I've done is replace the percent. It often is quoted in percentage, fractional percents, but I put that in milligrams per litre, parts per million. And so the bitter sharps and bitter sweets have greater than 2,000 parts per million of polyphenols in the juice. And when you go down to, and the sweets and the sharps less, it doesn't really matter how much less. But when you go down to dessert apples, so you just take typically 2 dessert apples, Cox, which we're very familiar with, Fuji, which is a worldwide apple, you see the levels are a great deal less. So the dessert apples have far less of these polyphenols in total than the key bittersweet and bitter sharp apples, which are the ones we're interested in cider making. And the other thing, sorry, Gabe. Yeah.
Well, just to say, so it's not to say that sharps and sweets don't contain any polyphenol at all. It's just considerably less than our bitter sweets and bitter sharps, but also tangibly the way that they sort of present themselves, it's not particularly overt relative to either maybe the presentation of sugar or acidity or kind of floral characters. But there are some that obviously have, you know, Cox is 700, which is considerably higher than Fuji, let's say. So there is also a range amongst dessert apples.
Yeah, that's a good point. In fact, maybe I've not really stressed that in the past, but you take, you know, some of the dessert apples do have useful amounts of tannin in them. It may not be perceived as really bitterness or astringency, but it'll be perceived as a sort of general mouthfeel, which is the key thing.
Yeah.
And Cox or Russet or any of those, or Ashmead's kernel, any of those types of dessert apples, which people favour for making cider when they are restricted to dessert fruit. And as you know, if you go to Australia or the US and Canada, you'll find people who are needing to use a lot of the standard dessert varieties, maybe not the standard dessert varieties. You wouldn't preferably use Fuji if you had a chance. But things like Cox and Ashmead's is very popular in North America. People plant it specifically for cider making, which seems odd to us on this side of the Atlantic. But then, of course, it's much more difficult to grow the bitter sweets and bitter sharps, more difficult to get hold of them anyway, whereas they can actually get hold of and manage things like Ashmead's quite well. So yes, so it's a continuum, really, I suppose. Anyway, the other thing I wanted to point out was that they are present in apples. The polyphenols are present throughout the flesh in a way that they're not in wine grapes. And people often think, oh, well, in wine grapes, you've got all the tannin concentrated in the skin and the red skin, and they don't have very much in the flesh. That's not really the case in apples. It's much more equally distributed. In an apple, the polyphenols are all the way through the flesh. more so than they are in grapes. Anyway. Okay, so that's the sort of general figures that you've got.
Sorry, just one question on that as well, Andrew, and I will I will let you speak.
Yeah.
There is, and I think we might have briefly had a conversation about this before. There are some people who have an observation that a careful, gentle pressing, or indeed like a free run of juice, produces some different constituencies into that juice rather than something that has been quite squeezed and extracted. Is that anything to which you've had any experience or insight on?
Not really for cider apples, no. I mean, I don't know if these are people using cider apples or people using dessert apples.
A bit of both, actually. A bit of both.
Yeah. I have to say, never really studied that in any detail because it's never been a factor that was ever particularly important. You know, in Britain, we've always had plenty of tannins from the flesh. I mean, just as a very slight diversion, when I was at Long Ashton, my Long Ashton days, we were looking to try and increase the amount of polyphenols in cider by fair means or foul. We were looking at using isopropanol, which is a common alcohol used in the food industry, to extract pomace and extract apple skins, to re-extract them with alcohol to get more tannin out of the pomace, to be able to put it back, at least in theory, to put it back into the cider. And it is a pretty harsh sort of tannin. You get plenty of stuff out, but it does tend to be fairly harsh.
Why was there the desire to increase, to try and really harvest as much phenolics as possible?
Well, this was back in the 70s when the cider makers sales were beginning to increase quite quickly, and there was a worry that there wouldn't be enough high tannin apples on the market in the UK to fulfil the demand. As it was, things changed because the marketing people decided that actually ciders didn't have to be as tannic as they used to be. Indeed. And so the nature of the product changed. So we didn't actually need all these high tannins in the end. But for a while, people were very vexed about getting more tannin out of what they had. Okay, so shall we go on then?
Please do, please.
Okay. So the roles of the polyphenols, the things that we want to look at. We've got these are the areas I want to go through. So we've got mouthfeel, volatile aroma precursors, colour formation, and then we've got other things, post-bottling haze and antioxidant properties. So these are the categories I'm going to look at in more detail now. So we'll start off with what we call mouthfeel, which is a good general sensory term for, well, mouthfeel really. I can't describe it any better, can I? What you get is as I mentioned before, you get this rather non-specific mouthfeel and body from the catechins and the phenolic acid. And if you don't have much in the way of tannin there, in these apples, say your point about Cox earlier is a good one. So something like Cox or Ashmeads will provide a bit of mouthfeel and body from the catechins and phenolic acid. You won't have an awful lot of prostaglandins. They will be there, but not large amounts. But that will still be very valuable and very useful to the cider, and that's why those sort of intermediate apples, as one might think of them, are still very worthwhile. But when you get to really, as it were, detectable bitterness and astringency, when the apples are real spitters, so you take a bite and you think, oh God, this is awful stuff. It's not anything that anyone would eat for pleasure. That's where the prostaglandins are really coming to the fore. And it turns out that what happens is that the bitterness is associated with the smaller oligomers, so with units of maybe 3 or 4 joined together. And the astringency tends to be associated with the larger oligomers, so anything up to, I said, the maximum soluble is about 8. So you've got that sort of a cutoff. And really, just to sort of underline the point that the only true tannins in apples in terms of being able to combine with protein, and this is, of course, combining with protein in your mouth in this particular context, are these prostaglandins. So I'll just go on to this. This makes the point that I just made in words, in that if you look at the degree of prostaglandin polymerization along this axis at the bottom here, and you rank it, you look at the bitterness, which is the solid line, and the astringency, which is the dotted line. and you have some arbitrary measurement of magnitude of taste, you see that the maximum of bitterness is achieved at somewhere around this prosanidin tetramer, 4 units joined together. But the maximum of astringency goes on rising pretty much indefinitely until it's no longer soluble, and it's not able to dissolve in the mouth anymore. And that's a general observation that doesn't only apply to cider apples, applies to wine grapes as well. And there are many research groups who have looked at this in different ways. For apples and grapes principally, but other commodities, perries for instance, they don't have, perries don't have any of the smaller units, they only have the big unit, which is why perry pears are astringent but not bitter. So that's the sort of universal observation that would appear in terms of fruits and their flavors. And that really comes on to this business between what we used to call, what we probably still call, soft tannin and hard tannin. So if you took two extremes that would be familiar to people who are familiar with it, with English bittersweet. So Tremlitz is a hard tannin because it's more bitter, and Dabinet is a soft tannin because it's more astringent. But you can easily find levels of Tremlitz and Dabinet with the same typical levels, say around 2,000 to 3,000 parts per million of total phenolics. But one of them is detectably more bitter than the other. So the Tremlitz is more bitter than Dabinet. And the question is, why does this happen? And the answer is because it contains relatively more of the lower molecular weight prosanidins. So if we go back to the previous slide, that just is this. So in a sense, the Tremlitz, which is bitter, is more in this zone, if you like. And the Dabinet, which is astringent, is more in this zone. But the total amount of phenolics is the same. It's just the distribution of molecular weight is different. Okay.
Sorry, Andrew, just one or maybe even two questions there. So in terms of, from my cider making background starting, certainly, the idea of wishing to try and oxidize the juice with the thinking and intention that it would help to reduce that hardness of the of resultant tannin within the end product. Is that something that holds weight?
Yes, to an extent. I'm going to come on to that in a minute. So
okay,
let's leave that for a minute.
We'll leave that one for a bit later. Yeah. And my second question was around maybe, and if we're going to cover this again, please do let me know. We're talking around mouthfeel and then aromas, etc. But are we going to be able to talk about taste at all? Do phenolics contribute towards taste in any way? Or flavour?
Yeah, I mean, are you distinguishing? Okay, so
from a mouth, obviously you don't taste astringency. It's more of a sensation.
No, all right, okay. Well,
bitterness would be similar to it.
Yeah, you look at the primary taste, the 4 primary tastes: sweet, acid, sour, and bitter. Then only bitter is a taste that we're recognizing in cider apples, if you like. In this context, as far as phenolics are concerned, obviously we're recognizing sweetness, but that's not relevant here.
Yes.
But as you so rightly point out, astringency is not a primary taste. And astringency is due to the way in which the tannins complex with the protein in the mouth, and they lock it up and they stop the mouth being lubricated by the normal proline-rich proteins in the mouth lubricate the mouth, and they stop it being lubricated. So suddenly everything feels terribly dry. So astringency is not a taste in the true sense. You don't have taste receptors for astringency as you do for bitterness and sweetness. What you do have is the fact it's an overall, it's effectively a tanning. You're locking up those proteins. And so your mouth feels incredibly dry because it's a physical sensation. But it's not in any way a taste as it is to do with taste receptor. Okay. When it comes to aroma, we'll come on to that in a minute, but they're derivative rather than primary. Okay.
Thank you.
Okay, right. So we've done mouthfeel now. Oh, we're coming straight on now to aroma precursors. because that's also to do with not so much the taste, but the flavour in general, and aroma. You know, the flavour is to do with the combination of taste and aroma. So here we're looking at the breakdown of phenolic acid. So I showed you before phenolic acid, chlorogenic acid. And the interesting part we're interested in is this part here, because under certain circumstances, this part here in green can split off from the rest of the molecule. And this phenol is these phenols are volatile enough to be able to be perceived as aroma. So they can have a very important role within the cider flavor, but they're derivative. They're made by breakdown of the bigger molecules, particularly the phenolic acid. So let's have a look at what happens here. This is normally done by enzymes in various bacteria, principally lactic acid bacteria. So lactobacillus, Pediococcus, Brettanomyces also, which is the yeast, of course, the spoilage yeast. They all have the enzyme system that will break down. So let me just go back a minute. Let me get this cursor behaving. That's not what I want to do. I want to go through this. Sorry, I'm making that with video. Sorry, previous and previous and previous. Right. So I was saying that the enzyme systems are breaking down this molecule at this point, and so this phenolic is being liberated into the headspace as the aroma. That's what I was trying to say. And that's due to these microorganisms here. They all have the same enzyme systems, even though the lactobacillus and the Brettanomyces are not related at all. They all have the same enzyme system. But Enococcus, which is the standard malolactic that you buy, if you buy a malolactic culture, it will be an Enococcus almost certainly, and is also found in the wild, of course. But that lacks this enzyme system for conversion. So you don't get that from Enococcus, but you do get it from lactobacillus. And the types of aroma you're talking about depends on the structure, but you're getting spicy, leathery, farmyardy, old horse, medicinal band-aid, all those types of things. Some of which you might regard as desirable, so possibly spicy, a little bit of old horse, we like in the UK. But if you're in the medicinal band-aid area, probably no matter where you are, either side of the Atlantic or the other side of the Pacific, you probably don't like those. But the point is that they're well, I'll come on to this next slide. Sorry, did you want to ask a question, Dave?
Well, my question is, these characters, these aromatic characters, volatile characters that are so closely associated with these kinds of apple varieties and are caused by changes within those phenolics, but caused by these particular bits of microflora. So, does the aroma come from the fruit, or does it come from the action of the microflora, or it's in terms of, you know, if your cider making program was one that was incredibly clean with regular high levels, ensuring that there's always good high levels of free sulfur, etc., that sort of kept that microflora quite low, would that inherently mean that even if you were utilizing Yarlington Mill and Dabinett and Harry Masters Jersey, that the volatile phenolic potential would be slim?
Yes, it does, because it's entirely dependent on breakdown by these other microorganisms, principally lactic acid bacteria,
right,
or possibly Brett. So yes, it's entirely dependent on that. So although the precursors are inherent in the cider apples, and there's still a lot more we don't really know in detail about, but the precursors are inherent in the cider apple. But to liberate the precursors, you have to have enzyme systems which are found predominantly in those bacteria. So if you have a very clean bacteria-free fermentation, you will not get those types of aroma, no matter you're working with Yarlington, Dabinett, or whatever.
Yeah, thank you.
Okay, so the actual chemical names are things like ethyl phenol, ethyl catechol, ethyl glycol. It depends on which actual precursors are being liberated, and there's quite a lot of complicated chemistry behind all that, which we won't go into. Now, as I say here, those flavors can be prized in low amounts by what you might call traditional cider drinkers. I know most of us in the UK know that, and we regard these as bittersweet aromas indeed. We call them bittersweet aromas, even though the aroma is actually produced by the bacteria. But then you get to a point where they become taints, and that is very much a matter of what you think of as acceptability. Now, if you're a New World winemaker, ethyl phenol is synonymous with bretty. They even have routine analyses for ethyl phenol, and of course they absolutely want to keep it out of any of their wines, and that's spilled over into cider making as well. So they would regard, I think many people in the New World will regard these types as taints sooner than we would in the UK, or in Europe, I might say, because for instance, you look at many traditional red wines, they say the same thing happens in red wines. So you take a traditional red wine from south of France, particularly made with a grape like Mourvedre, for instance, the Bandoles, things like that. They have a lot of these flavors. We don't think of them as bretty or unpleasant. They're characteristic of the wine, but a lot of New World winemakers have difficulty in accepting them. So what we're talking about is that the actual levels we're talking about, the transition between acceptable and unacceptable is very low. It's in the region of 1 part per million before you cross over. There's some French work looking at this in Ciders, which was done about 10 years ago, which is quite interesting, with a lot of sensory analysis. So the transition is around 1 part per million, where it goes from being pleasant and acceptable to unacceptable. The other point to realise, is that the conversion rate is very low. We're looking at single parts per million of these aromas, but you've got hundreds or thousands, or well, let's say hundreds of parts per million at least, of the specific precursors. So the conversion rate is very low, and that makes the whole thing extremely difficult to study and to understand and to control. And as I said at the bottom here, the knowledge of how to control these aromas, how to control them routinely, reproducibly, reliably is very poor. And people find what works for them and it doesn't work for somebody else. And it's a big area which is still a difficult one, which is why so many people, I think, are saying, oh, it's too difficult to manage. We'll just bung in the SO2 and try and stop it happening completely. And I think that's one way you could look at it from the commercial point of view, because you can't control it very well. Okay, so that's that particular issue of the volatile aroma precursors. And then another major thing that the polyphenols are involved in is in colour formation. So let's look at that. So with colour formation in an apple, it's the oxidation of colourless phenols to form coloured quinones. So here's a little diagram. The phenol would have OH on those positions there. But in the presence of, after oxidation, it becomes what we call a quinone, like that. And those quinone structures have colour associated with them, really because of the electron delocalization around the whole of that ring, but you don't have to know that. But that's why they become coloured, because they form quinones. And this happens in apple systems, or not only apples, but apples is the primary example, by an enzyme called polyphenol oxidase, because it basically takes the polyphenols and it oxidizes them to the quinones, and that's an enzyme. It's a bit more complicated than it might appear. I'll go very quickly into this diagram, but don't spend too long on this. But it's a so-called coupled oxidation that happens. What happens is, here's the polyphenol oxidase enzyme, and it's picking up oxygen from the air or the environment, polyphenol oxidase, and it's oxidizing chlorogenic acid, one of the phenolic acids, and it oxidizes it to chlorogenic acid quinone, and the quinone, when it then regenerates back to chlorogenic acid, but in so doing, it then oxidizes the colorless procyanidins to colored oxidation products. That's why the whole thing is a coupled oxidation. The procyanidins don't oxidize directly, they have to have the mediation of something, another phenolic in the way to make the polyphenol oxidase effective. Because the polyphenol oxidase can't actually work directly on the proteins. But that's all I'm going to say about that. It's really quite complicated. Anyway, look at color product formation in real life terms. As we know, all native apple fresh phenolics are colorless. You know that. You bite open an apple, cut open an apple, it doesn't have any color. The color derives in the next few minutes as the phenolics are oxidized by the polyphenol oxidase and into these different shades that we're familiar with: yellow, orange, brown, all those sorts of hues. And everybody knows that. You know it from childhood. But the amazing thing is the structures of these, the end products, the structures of the yellow, orange, and brown, they're still not known. They're just so complex. It's almost impossible that you'd ever discover what truly the exact structure of these things is in chemical terms. But what we can measure is the color changes and the phenolic changes that we can see and measure ourselves, even if we don't actually know what the true structures are. So here's some work which I'll just take you through about oxidation. So here you've got, we're taking some juice, all right? And we've got, we're oxidizing some juice. That's one thing we're doing. We're also making juice from some pulp which has been about in thin layer and oxidized. And what we have measurement here, so-called chroma, is a measurement of the color. All right, so the higher up the scale it is, the more color it has. And if you take a juice, which is pressed quite quickly, and you oxidize it for several hours like this, and you see the juice color goes up. It goes up a fair way, and then it sort of plateaus off, and it stays at that particular level. So that's what we're fairly familiar with. The juice will become more colored as it sits around because of the enzymic oxidation. But if you then look at the juice, you have to make this happen. If you then look at the juice you get from the pulp itself, the color level reaches a maximum fairly quickly after maybe an hour or two. Hugely depends on the variety and temperature. And then the color disappears again. So it gets taken back onto the pulp, and effectively it's reabsorbed back onto the pulp. So it depends, the color you eventually get in your juice is really quite dependent on whether you aerate the juice as juice or whether you allow the pulp itself to oxidize. So that's a way of determining color. Let's go on to the next pair of this one, which is here, where we're looking at not so much the color itself, but the phenolics that are left. It's exactly the same system. In the juice system, the phenolics actually don't change. They stay pretty much the same because there's nowhere for them to go. They're sitting in the juice and they can't disappear anywhere. Eventually they can drop out of solution. But on the pulp, the phenolics start off at a high level and the pulp phenolics drop really quite quickly and stick on the pulp and you can't get them off again. And at the same point, if you remember, if you go back to the previous slide, and there was a peak of color at this point. As the phenolics are dropping, you get a peak of color, but then that all disappears and it gets absorbed back onto the pulp. So the point is that the way in which you handle the juice or the pulp with respect to oxygen can determine the color of the final product, of the final juice, quite markedly. And that's what people do if you want to, you have that way, certainly with bittersweet fruit, of manipulating color. If you wish to manipulate it, you can also, of course, because you remove the phenolics while you're oxidizing on the pulp. If you don't have it so much these days, but in the old days when you got very high tannin fruit, people wanted to get rid of some of that tannin. It was just too fierce. And so if they allow the pulp to oxidize before they press it, then those phenolics are going to drop. And people who still do that, of course, are perry makers. If you've got some of those really high tannin perry pears, and you want to get rid of some of that tannin, you macerate those pears not the only reason you might macerate, but that's one of the main reasons. You macerate those pears and you remove a lot of those phenolics, so they're nothing like as astringent, so that the system becomes much more obliging. Sorry,
Andrew,
yeah,
a couple of quick things here. Firstly, we're having a little bit of trouble hearing you. I don't know whether your microphone is able to get it.
Okay, sorry. Maybe
that's
I'm
all right. No, it's all right. I know that you're having the weather's a bit challenging down in Oxfordshire today.
Yeah, we had 2 power cuts already.
2 packets. So we've done well to get this far. So I'm a happy chap. My second point was going to be around. Have you come across or tasted? There's a prevalence of 1 or 2 in the UK and increasingly more so in North America of ciders made with red fleshed apples where the colour has been retained through fermentation and presents itself as a pink or indeed sometimes presented as a rosé cider. It seems quite a challenging thing to hang on to that coloration. Why would that be?
It is very challenging because these are different compounds from what we're talking about, because they were the group of compounds I said at the very beginning, the anthocyanins, which are primarily in the red skin of the apples, which I wasn't going to talk about. And the point is that there are some red flesh varieties, as you know, and the colour is, the pigment is the same in the skin as it is in the flesh.
Okay.
And yes, it is extremely difficult to retain that colour because it's the polyphenol oxidase will attack it, and it's in a relatively low concentration, say compared to red grapes. Once you've done the skin extraction of red grape, it's still a pretty low concentration, and you will find that they are very labile, and it's very hard to maintain that colour. There are ways around it, which is a whole game in itself, which I'm not going to go into now. But it's very difficult to maintain that colour, I have to say. And good luck to anyone who manages to do it. But it's a different mechanism from the one I'm talking about here.
Of course. Apologies.
Because the compound. No, it's a good question though, because what it's more akin to, of course, is making red wine from red wine grapes, and the chemistry is kind of similar to that. But because there's so much more in red wine, once you've done the fermentation on the skins anyway, then of course it's a different thing.
Super.
Okay. Let's move on to, generally, a sort of summary of pulp oxidation is a place where you can gain or lose colour depending on how much oxidation you allow. You can lose the phenolics, most tannins, if you wish to lose them. So if you do wish to lose them, it's a good place to lose them. If you don't lose them, then don't lose them. It's affected hugely by things like the apple itself, by the pH, by the level of polyphenol oxidase, than the phenolic levels. It's a very difficult one to predict. And then the colour increase you get as the oxidation takes place is partly reversed by SO2, as you probably know, and also during the yeast activity during fermentation, the yeast lightens the colour quite a lot if you actually measure it, because the quinones are being, the oxidized quinones are reduced back to polyphenols. That's what happens then. Can you still hear me all right? Am I coming better?
You're a little bit better. I think it's just not a very good line, unfortunately. But that's okay.
I'm shouting a bit more to make sure you can. All right,
that's very kind. But the presentation helps immeasurably as well. So don't.
All right. Thanks for that.
Don't lose your voice.
All right. So now I wanted to look at post-bottling haze as another polyphenol role. So this is to do with the polymerization of the prostaglandins. So you've got these units up to about, from sort of 2 to 8 units in length. And then once they're extracted from the juice and they've got into the cider, they can then polymerize further. So they join up with each other more. So they can either join amongst themselves, they can polymerize amongst themselves and just go into longer chains. They can link up with protein if there's any protein around in the solution. So that's another thing they can do. And they can also link up with acetaldehyde, which is coming as a primary product of the yeast fermentation. So the gradual drift is that during cider making, although you start off with these prostaglandins being a fairly defined chain length, as time goes on, they will get bigger and bigger just by these processes. And unfortunately, those sometimes manifests itself as a chill haze, which means that although they're soluble at room temperature, then when you put the cider in the fridge, they come out as the sediment. Sometimes it will go back into solution, sometimes it won't. But that's been a chronic problem for the industry over many years, and people used to get rid of it with primings or polyflower, or, of course SO2 does help to stop the polymerization as well. And to some extent, ultrafiltration retards it because you're taking out some of the units which are about to polymerize and come out of solution, and you give a bit more, you've got a little more breathing space then. But it's, in a sense, to say it's a chronic problem. It was always going, it's always possible that it will happen. And it's one of those things you sort of stay on top of as best you can. But it's not an easy one to prevent necessarily. And then the final role really is the antioxidant and pro-oxidant properties of the polyphenols. Now, polyphenols are antioxidants, that's the fact. They take up the oxygen and they become converted to quinones. But as they do that, in some cases, they can actually produce hydrogen peroxide as a byproduct of the enzymic reaction. And so once they've generated hydrogen peroxide in the solution, it's only tiny amounts, the hydrogen peroxide is then a very active pro-oxidant. So that can then oxidize the alcohol, the ethanol, as we precursor, can oxidize the ethanol to acetaldehyde. So you then get these sorts of sherry-like aromas in the cider. And that's principally in ciders which have been affected by the air. Where the air has got in, the polyphenols are oxidizing, they produce hydrogen peroxide as a byproduct. The hydrogen peroxide oxidizes the ethanol to acetaldehyde, and hence the sherry aromas. It's a purely chemical process. It's not a microbial one. However, it can go on at the same time as microbial processes, which makes it difficult to disentangle. But a lot of it is purely chemical. And again, fortunately, it's inhibited by SO2 because the SO2 will immediately scavenge the hydrogen peroxide. And so if there's enough SO2 present, that won't happen. I mean, it's the fault in the sense that you shouldn't let the air get at your cider, basically.
Yes, of course, just standard good cider making practice.
Just standard good cider making practice. Yeah. Whereas things like chill haze, these are kind of bad luck as well.
There's a question. If anybody does have any questions, please put it into Facebook. And for the next, 15 minutes or so, we've got plenty of time for a bit of conversation. I'm also being told, Andrew, that everyone can hear you and us just fine. It's my very bad old laptop that I think that's
you and me that haven't
we do have a question that's come in from Rory Suter from Cotswold Cider Company. Does the bottling haze matter other than it's being an aesthetic issue?
Well, no, it doesn't, does it? It is purely aesthetic, but on the other hand, it can make the product look quite unpleasant. There's one, well, I think we can tell you who it is. You remember when Aspel Cider years ago started to get into the cider vinegar business? Yes. And they had a lot of problems with post-bottling haze for quite a while. And finally, John Guild, who was then running the business, hit on this brilliant idea. He said, well, what we'll do is we'll turn this liability into an asset. He put a label on the bottle saying, if this fine product produces a sediment, this is a sign of its quality. And you should be pleased by this, And he turned one. That's the point. He was trying to make it. He was trying to turn it from a problem into an asset.
It's very
that won't work in all markets. That won't work in all markets.
Of course not.
Obviously, people expect things to be starting nuclear, unfortunately. Sorry, that was a question for Rory, wasn't it? Okay.
It was, yeah.
So now we're moving on then. What's next? Oh yeah, we're looking at how much overall with the phenolics. How much have we got? Well, we've looked at some figures already, so I won't focus on this very much, but it's impossible to measure, or very difficult to measure all the phenolics individually, as I said. You can make a very rough assumption but the non-tannins are about 40 to 60% of the total, and the tannins are about 60 to 40. So roughly 50-50, but you know, that's basically what I would say is roughly 50-50 between non-tannins and tannins, between phenolic acids and procyanidins. Now, the data we usually see quoted is derived from the Folin or the Lermontale methods, and it's quoted as total polyphenols in the juice. And those are the figures you normally see. You really don't have the possibility in real life to measure all these individually. And in fact, a lot of people never measure tannin anyway. But if you did need to do it, those are the methods that are used. The Folin is widely used in the wine industry, or Lermontale, which is a bit old-fashioned, but these are used Long Ashton. So those are the way you would sort of discover how much you've got if you needed to put a finger on it. Sure. Now, phenolic content is primarily a variety of character. As we said, it relates to the particular apples. When you look at the cider apples, even if you've got a high bittersweet, a heavy bittersweet, and a low bittersweet, they still typically have the same relative composition as the same, even though the absolute is different. There are a few exceptions. Yarlington Mill is the well-known exception, which has a much higher level of phenolic acid and less tannin than you'd expect. So when you look at the figures for Yarlington Mill, you say, oh, that's a heavy bittersweet. But in real life, it isn't a heavy bittersweet because it's got a much higher level of phenolic acid and it's less tannic than expected. Now, the other thing about Yarlington, as many of us will know, is Yarlington is one of those that tends to give the spicy, bittersweet aromas more readily, I think many of us would agree, more readily than other bittersweets. People talk about, oh, it's got Yarlington character because they can smell it. But in fact, what that is, as we said, it's coming from the breakdown of phenolic acids, but I don't think it's an accident that it has higher levels of phenolic acids, relatively speaking, in Yarlington to the rest of the tannin. So I think there's a connection there, although it's never been formally studied as far as I know.
It's a fascinating thing that there are maybe a handful of varieties that have certain sensory characters that to a trained nose, one that's done a bit of quality control, there are certain varieties like Yarlington, maybe like Dabinet with that, you know, intense sort of orange juice kind of character, or Kingston Black sometimes with it, you know, very often Kingston Black can present as having a little bit more of the, if not full Band-Aid, but some of that medicinal kind of quality. It's interesting how maybe the phenolic composition is, maybe it's the important part and the signature, the ident of those important varietal characteristics.
Yeah, we really don't understand much about those varietal characteristics, I must say, because although we understand the outline of how those aromas are produced, what you don't really know is what's leading the bacteria to work in a particular way. Are there other micronutrients or other materials within those apples which are changing the way in which the pathways are acting? We simply don't know. It's too detailed and it's never been studied, which it would be a very interesting one if anyone's able to. And now, so that was about the cultivars themselves, but there's also the effect of the environment. So phenolics tend to be diminished. So in certain conditions, if it's warmer, they tend to be less. If you have more nitrogen available to go into the tree, they tend to be less. So if you're managing for a higher fruit yield, then the phenolics, by and large, tend to be rather diminished compared to if you're not managing in that way. Conversely, phenolics are increased by greater stress on the tree. So if it's water stress or heat stress or physiological or pest attack, that tends to increase the phenolics. But they're really complex and they're really interactive, and there's often very little you can do about it. It's just a fact that when it's a given in a sense, depending on where you grow your fruit, you just have to work around it.
So one of the bits of sort of received wisdom is that the cider and the sort of the tannic structure that one gets from an old tree, an old orchard, is either bigger or bolder or smoother or more pronounced or more complex than that from a younger tree, which may be linked to the increasing nitrogen uptake possibly, or those younger trees whereby they're putting a lot of energy into growth and maybe less into the into slower fruit formation possibly. But I suppose again that's just an anecdotal thing. But
yeah, I think there are two things. One of them is the effect of nitrogen on fruit growth, and so that I don't want to go into too much detail on this, but it's to do with the amount of sugar you have available. And if you've got not very much nitrogen available, then that sugar is available to be turned into phenolics. If you've got a lot of nitrogen available, that sugar tends to go into protein, in other words, plant growth. So that's where the relationship comes. And that relationship has been shown for wine grapes as well. It's not, and other fruit crops, it's not just apples. The other thing, of course, is that if you've got increased nitrogen and you're not adding nutrients to your fermentation, the fermentation will be faster. So that will give you a different aroma spectrum from a slower fermentation. So that's putting another level of complexity on top of all that.
Of course, yeah.
So there is an effect of the environment, but it's very complex. And by and large, it's one you can't really predict, or you sort of work around it. You manage it in your own place, as it were, to get the best out of your fruit. And this is just to demonstrate the effect of the environment. This is some work we did many years ago from Long Ashton. You can see 1973, 75, 1982. We took a set of orchards, Walmer's orchards at Mornington-on-Wye, and we were looking at the same trees. We were harvesting apples from the exact same trees over 10 years. And we were looking at the tannin variation in these trees over time. And what you see here, we were looking at tremolets and davenant, it so happens. And what you see is a big variation year on year for no particular reason. And they don't even go in step. You know, okay, so that's fine, you know, those two are together, but then why on earth is that one, that year, that one, the tremolets was very high and the davenant was very low? We have no idea why, but it's just, so I can't explain the nature of this variation. All I can say is that there is an environmental variation, and these trees were all growing in the same orchard on the same plot. But the tremolets and the davenant were experiencing exactly the same weather conditions, and yet they're coming up with different tannin levels year on year, and it's varying quite a lot. And the CV, if you're into statistics, is quite wide, 25%. That's quite high. It's quite a big difference. So, you know, and we don't really know how that's controlled or why that's controlled, unfortunately.
There's a couple of people pointing out rightly that 1976 was obviously the previously to 2018 was the big hot dry summer.
75 and 76, which I remember well, were the hot dry summer. Yeah. This is absolutely true. 76 worse because it was a drought year following a very dry year. But that still doesn't explain why the huge difference between tremolets and davenant. So yes, it explains the fact it's extreme, and oddly enough, I mean, you can't go into
1977 is the same, if not higher.
So that makes no sense.
Yeah.
Anyway, I think that's the end of the formal part of the presentation.
Super.
Yes. So if we've got any more questions.
Yeah, there's a couple more that have come in. Max Noel, Steelhead Cider, and the legendary G. Noel. Max.
Yes.
Good to see you. Max asks, so if you want to maximize color by maceration, does this inevitably reduce the tannin or the tannic characteristics, and vice versa?
Almost inevitably. Well, no, because you could go back to that kind of that sweet spot. Let me go. Hang on a minute. What have I done? Oh, I entered them. Let me see if I can go right back.
You should be able to do it via your up arrow on your keyboard if you're on the.
Thank you.
If you're on the keyboard.
Let's see that. No, it's not working. It might work on the. There, it's doing this one. The left arrows.
There we go.
There we go. So, okay, so we're getting the maximum amount of color from oxidizing on the pulp. Say in this particular case, with this, it was an experimental design. after 1 to 2 hours, you're getting the maximum amount of color. Okay. So then the amount of phenolics is somewhat diminished, yes, but it's not as diminished as it might be if you went on the whole way. So there's a sense that there's an optimum level of oxidation. So you'd allow maybe an hour's worth of oxidation. That will very much depend on the variety. It depends on the temperature. It depends on how thick or thin your layers are, how much oxygen you get into the layers. So a thin layer will oxidize more quickly than a thick layer. But there is a potentially an optimum region here where you could reduce the phenolics by a certain amount, but you can still get an increase in color. But that is going to be part of the skill of the cider maker in understanding that and deciding what to do. There's no amount of real instrumental measurement that's going to tell you how to do it. You're just going to have to suck it and see.
We have a question from Georgia, and I'm gonna say this very carefully. For small scale production, how might the use of a slow masticating juicer affect phenols versus using a traditional wood cider press? There's a question for you.
Yeah, and I don't really have a good answer because I've never used a masticating juicer. I'm aware they exist, but you don't see them here hardly at all. I suspect, and this is only a guess, but because there's a masticating juicer, you're grinding up the pulp quite a lot. And I suspect you're getting quite a lot of oxidation on that pulp as you do it. And I suspect you may lose quite a lot of tannin during the mastication process compared to conventional mill and pressing. But honestly, that's just a guess because I've never used one and I don't know.
Super.
That's all I can say.
Jeremy from Herefordshire says, I recently enjoyed a very softly tannic tremulous bitter. Could this lack of bitterness be due to oxidization of the pulp pre-pressing?
Yes, good. Yeah, it's a good thought. In fact, something I haven't mentioned so far is that, in fact, as the oxidation proceeds and as the polymerization proceeds, so you're losing stuff in total, but as the oxidation proceeds, the polymeric forms because they get bigger, they get more astringent. So you can change the bitterness and the astringency balance. And that's what happens during wine aging, for instance. When you take a red wine, the young red wines can be very bitter as they age in bottle. Let's say we're talking about aging in cask or in bottle, maybe in cask, with slight amount of oxidation to encourage polymerization. You lose the bitterness gradually and you get the astringency. And this could be happening with tremulous. If you work with that tremulous in such a way as to encourage polymerization, the total tannin will drop, but also the balance of the bitter and astringent principles will change. So it will become more astringent as time goes on. Yeah.
There's a question from Manfred in Germany. He says that I added a portion of Perry pears to one of my ciders and a lot of protein was falling out even when the speed of fermentation was slowing down. Is this comparable to keeving?
Well, if he says Perry pears, and you really are Perry pears.
Yes, there are quite a lot of very high tannin in West Germany and Luxembourg and Switzerland.
Yes, I know. If they truly are Perry pears, it's really nothing to do with keeving, which is to do with pectin. It's much more likely to do with tannin. And it's that high tannin, and anyone who's made Perry from high tannin Perry pears, or even not those high tannin Perry pears, knows about this white milkiness that you get.
Is this the legendary fried egg that comes out?
It might be called a fried egg.
Well, that's what I call it anyway.
Yeah, but you can get this, and this is the bane of Perry makers to an extent, is when you've got this polymerization of this particular Perry tannin, and it drops out of solution, or rather doesn't drop out of solution. It sits there. It's become insoluble, but it sits there as a white milky haze in the Perry. It can be very, very difficult to get rid of. But it's nothing to do with pectin or keeving. It's purely to do with tannin polymerization.
Super. Lucy, I know that you've got apparently quite a long and specific question for Andrew. You can email me the question and I will pass it on to Andrew, no problem at all. Well, that's it in terms of questions. Oh, we also had Jez Howard, who said that he's bought Kingston Black from Somerset and also from Southampton, and the two were both incredibly different in acidity and taste. Is this down to the fabled? It's a term that I know that some cider makers don't necessarily like, the terroir, in terms of how the landscape, the soil, the underlying geology, the angle of the slope that potentially does have an impact upon the way that the fruit presents itself. That's,
Yeah,
again, something I suppose that hasn't had a lot of time or research into it.
No, it hasn't, and I think Jez is right. I think terroir is probably the critical thing there, because the soils in Somerset and the soils in Hampshire are going to be different, and the environment will be different, and it's surprising how different the apples do. I mean, even I grow my bittersweet apples here in South Oxfordshire on very thin chalk, and they never ever reach that full, rich, bittersweet character which I was used to in Long Ashton, which you get from Somerset soils. Yeah. And we're only 80 miles away, but the soil types are so different. Yeah, there's definitely an effect of terroir, no doubt about it in my mind.
And obviously, increasingly all around the world, there are orchards that have been planted up with different sort of tannic, phenolic forward apples. The wonderful, sadly missed Drew Henry of Harcourt, just north of Melbourne, planted up his orchard in the mid-90s with all of the apple and a lot of peri pear varieties that we would know, with some really interesting results coming out as well. The guys, is it Red Sails? I forget the name, on Tasmania.
Yes, Clive.
They again, another old orchard, and obviously Steve Wood and all those onwards in North America. If you've got anything interesting or anecdotal about how those varieties fare in different climes, or
only in a very general sense. I mean, I visited Drew Henry and tasted some of his ciders, and what was interesting is that generally the tannin levels for the same variety, the tannin levels were lower, even the heavy bittersweet, because the weather in the Melbourne area is better than it is for us. Not a huge lot better, but just it's a little bit warmer in the summer and not so cold in the winter, and you get. And also you get more sugar produced. You've got higher alcohol and lower tannin for the same type of apple. I think in Tasmania it's very similar to us, and it's very difficult to put much between us and Tasmania. But also I've had some ciders. I've related this frequently. I had a cider once, the Kingston Black, grown in the Napa Valley in California, and it was nothing like any Kingston Black that you would ever get from this country. Very high in alcohol, very little. It was interesting, but it was not Kingston Black. There's no tannin to it at all. But so I think, terroir is a very interesting and important thing to consider, particularly when you're planting in new environments and new locations which have not traditionally had cider apples in them before. Have not had European cider apples in them before. Sure.
Absolutely. Andrew, I think that we're just about at the end of our time. Thank you so much for giving your time. If anybody who's watching, bear with me, who hasn't got a copy of Craft Cider Making by Andrew Lee out now, third edition. Cool. People still don't know how to make cider. It's amazing. It's a tome. That's tucked away in most cider makers' drawer, I would hazard a guess. It certainly was when I was at Weston's and when I was in New Zealand as well. It was always something to turn to. Andrew, so thank you so much for your time. We've had a very positive response on Facebook, and so I hope that you'll be able to maybe to join us again sometime if we continue into the future more technical events, and certainly for CraftCon next year we very much hope. So yeah, thank you very much for your time, and for everybody who watched, thank you for your time as well. Like I said, this is the first in a series of 4 weeks of seminars here on the Three Counties Cider and Perry Association's Facebook page, 4 o'clock every Wednesday. Next week we have Lorraine Boddington from the National Association of Cider Makers, coincidentally, who are also very kindly sponsoring these webinars. Lorraine is the newly appointed Technical and Pomology Manager for the NACM. So Lorraine's going to give a little bit of an update about what activities are being undertaken by the NACM, as well as a bit of a general update on what matters are sort of pertinent within the industry. So do tune in Wednesday, 4 p.m. UK time to hear Lorraine, and then we'll give you more information about what's coming up for the weeks ahead. But for now, Andrew, it's time for a cider for me. I don't know about you, so I'm pretty thirsty.
Okay, thank you very much, Gabe, for your chairmanship.
Our pleasure. You're very, very easy to chair. So thank you, everybody. Andrew, everybody, have a lovely day. All the best.
Bye for now, everybody. Bye-bye.
Bye-bye.